All right, so this unit is going to be on differential equations specifically, and today we're going to be talking about slope fields. So let's start with this opener. It says find the general solution to the differential equation s prime of t equals 4. And we've actually done problems like this before, where you're given a differential equation and you have to find the general solution. All this means is a differential equation is an equation of a derivative. All you have to do is take the integral of both sides with respect to t in this case, because it's s of t. And on the left side, the integral of s prime is s. And on the right side, the integral of 4 is 4t plus c. Easy enough. So visually, the general solution is any one of these. It represents, I should say, any one of these lines with slope 4. And when we first started doing integrals, this is how we learned them. We solved a differential equation and graphed out a graph that kind of looked like this one here, with all of these potential solutions. Okay, the next one says find the particular solution to the differential equation s prime of t equals 4 given s of 3 equals 4. So we already solved s prime of t equals 4, right? So now we just want to find what that c value is equal to for this particular situation when s of 3 equals 7. So all you have to do is plug in s of 3 equals 7 equals 4 times 3 plus c, and c is 7 minus 12, or negative 5. So our particular solution to this differential equation is s of t, is equal to 4t minus 5. Okay, so that would be like this graph right here, assuming that that goes through negative 5. Okay, the last thing we're going to talk about, finding general solutions can sometimes be challenging. And if you think about it, right, if you're given this differential equation, dy dx is equal to xy plus 2y, and it's like, okay, great, integrate both sides. I guess we could do our best here, and actually we will find a way to do this. We will figure out a way to make this look nicer. But one thing that we're going to learn how to do is to use slope fields, sometimes called direction fields, although I'll be honest, they're mostly just called slope fields, to visualize what exactly this looks like. So what we mean by that, we've got this graph, y prime equals 4. And remember, all that means is dy dx equals 4. So in other words, the slope is 4 at any point. And that's what we set up here when we said s prime of t equals 4. That's the same as saying the slope is 4 at any point. So in our slope field, we just draw like little tiny tick marks to represent the slope at any particular point. And there's an infinite number of these. I mean, I could go on forever. But each one of these slopes is equal to 4, and this represents a slope field. So if I just picked a random point, well, my line goes through this point here. This is what that line looks like, because it's following along with that slope field, because we know that slope is 4 everywhere. Okay, so that's a very basic example. We're going to get into slightly more complex examples. So if we look at this first one, and this was the packet that I handed out to you after your test, either on Tuesday or Wednesday, it says draw a slope field for each of the following differential equations. Number 1, dy dx is x plus 1. So basically it's saying that the slope is dependent on the x value. The slope is dependent on the x value. So one way to do this, and you don't have to do this for every single one, but just to give you an idea of kind of what I'm doing here, I'm going to say xy and I'll say dy dx. Okay, so when x is 0, y can be anything because, again, this derivative equation is only dependent on x. So when x is 0, I plug in 0 into that derivative equation and I get 1 out. So everywhere where x is equal to 0, I know that I have a positive slope of 1. Okay, so when I draw these slopes at x equals 0, I'm not, like, here's the thing. Technically, a slope of 1 is like that. It's from one point to its diagonal point. But that's not what we're concerned about. We're more concerned about the slopes in relation to each other. So, for instance, when x is equal to 1, dy dx is equal to 2. So I just need to make sure that when x is equal to 1, that these slopes are all steeper than the ones when x equals 0. And likewise, when x is equal to 2, I need to show that those are steeper yet, right? Because our slope is equal to 3. Again, I'm just plugging the x values into x plus 1 to find my slope. And when x is equal to 4, or 3 rather, my slope is equal to 4, which is even steeper. So we want to show, that one could be better. We want to show that the slopes on the vertical are all parallel to each other, and that in relation to each other, as we move to the right, our slopes get steeper, and as we move to the left, they get less steep. At 0, the slope is equal to 0. At negative 1, rather, negative 1 comma y, the slope is equal to 0. And at negative 2 comma y, the slope is negative 1. And those slopes are all the same as each other and negative, and they get more negative as we decrease x. And that's our slope field. That's our slope field. So if I said sketch a graph through, sketch the graph through point 0, 0, well, you'd go to 0, 0. Let me do this in pink. And we know it goes through there. And we know that the slope is 1 right there. And if you look at the general shape of this graph, what are you seeing? Right? What shape are you seeing? Hopefully, you're seeing a parabola, right? We can kind of see the slopes are negative to the left, and then they go to 0. And then as x increases and we move to the right, the slopes go positive. So hopefully you're seeing that we have a nice parabola. So this would kind of be like our sketch of the graph through the slope field. You can see how it just kind of, those individual tick marks kind of guide the graph itself. Okay, likewise, let's look at number 2. We have dy dx equals 2y. So now your slope is dependent on y. What I always like to do is, okay, I look for where it's 0. So everywhere where y is equal to 0, my slope is going to be equal to 0. So everywhere y equals 0, my slope equals 0. So I've got a bunch of zeros there. And then as y increases, my slopes become more positive. Right? And you'll see when it's all in terms of x, all of the slopes on a vertical are the same. When it's in terms of y, all of the slopes on the horizontal are the same. And the next problem, we'll look at what happens when it's in terms of both x and y. But for now, let's finish this off. So they get more and more positive slopes as y increases, and as y decreases, it becomes negative. And again, this doesn't have to be perfect. It's just, what do they look like in relation to each other? Are the horizontals roughly parallel to each other? And as we compare the graph going up and going down, are they getting more or less steep? So this graph, this kind of looks like an exponential graph, right? If you were given a random point, depending on the point that you were given, it would either look like this or it would look like this, right? And we can see that horizontal asymptote at y equals 0. Okay, now let's do number 3. We're going to do number 3, and then I'm going to close this video. I'll make sure that you have the solutions to 4, 5, and 6 posted on Canvas for you. So now we're in terms of both x and y. So what we got to do is actually plug in both x and y. And at first you might be like, oh gosh, this is going to take forever. I have to test every single one of these points. Well, let's look for some patterns. Let's see if we can find patterns. At 0, 0, our slope is 0, right? X is 0, y is 0, our slope is 0. As we go up in y, as y increases, our slope is going to increase. So this is a slope of 1, this is a slope of 2, this is a slope of 3. And my trick to you, I guess my piece of advice is never start your slope too steep. So don't be like, oh, this is a slope of 1, because then you're going to get into the problem where you're like, and this needs to be steeper, and this needs to be steeper, and it's like eventually you're going to have these vertical tick marks. That's going to be a little challenging to compensate for. So just kind of like, just make it ever so slightly positive, ever so slightly more positive, ever so slightly, you could go a little more than that, ever so slightly more positive than that. Okay, let's look at 1, 0. So x equals 1, y equals 0. There we have a slope of 1 again. Slope of 1 again. And you'll notice these are both slopes of 1. Okay, well, they exist on a diagonal. Let's see if that pattern holds true. Let's look at 2, -1. Well, 2, -1 is this point here, right? X equals 2, y is -1. And when we plug that into our equation, we get +1 again. Interesting. Okay, then we look at 3, -2, and we have +1 again. So it looks like we're getting the same slope on the diagonal, and that's exactly what is happening. So we want to make sure that those diagonals are all roughly the same slope. And then they get slightly more positive on this diagonal, slightly more positive, and then slightly more positive on this diagonal, and then slightly more, and you get the idea, until we're most positive at 3, 3. All right, let's look at our negatives. Well, actually, we know 0, 0 has a slope of 0, so 1, -1 is going to be a slope of 0, 2, -2, 3, -3, -1, 1, -2, 2, and -3, 3. So that's slope of 0, slope of 0. Again, all of our diagonals appear to be the same. And this won't always be the case, but it's good to look for those patterns that will make your life easier. Okay, and then it's -1, slope of -1, -1, -1, -1, -1, and then more negative, and we continue that pattern on the diagonal until we get to the most negative. So again, depending on the point that you are given, this graph kind of looks like, let's see, if we're given something up here, this graph would look like this right here, right? But again, it depends on the point that you're given of what your slope field looks like, right? Like if you were given this point here, well, your slope or your particular solution is going to look something like this, right? So it all depends on the point that you're given. Okay, I leave the rest of these 3 for you to do on your own. I'll have the solutions posted on Canvas. I also want you to complete the multiple choice problems on the next page through 15. You do not need to do anything past 16, 16, 17, 18, and 19. We will do those together in class. Okay, so I just need you to do the problems on this page. And I will have those solutions on Canvas as well. All right, I hope you enjoy your days off, and thank you for giving me your time.